Right, relatively short section compared with 16.1, looking at activation energies. Talked about them a little bit in topic 6. Just going to look at how to maybe work them out in this unit. So this is what we're talking about, and as you can see here, there's going to be a little bit of maths, a little bit of graph plotting perhaps, to try and work out what these activation energies actually are. So this is our Arrhenius equation. Never sure if I'm saying that correctly. And you can see we've got a link between rate constant, this A, which as you can see down here is described as a frequency factor, so the frequency of collisions with proper orientation. So we said right at the start that we needed a collision of sufficient energy, our activation energy, but we also needed to be the correct orientation, so that's what this A is relating to. And then we've got exponential power minus activation energy over R, which is the gas constant, 8.31, and T is our temperature in Kelvin. So if we do a bit of maths on that, we can actually expand it to this, and that is now of the form y equals mx plus c. So if we have this as our y-axis, and if we have if we have x as 1 over t, then our m is minus EA over r, which you can see here, and our intercept, y-intercept, if I was to take that back to there, that would be ln A. So we can use this relationship, assuming we've got rate constant values, as soon as we've got the temperatures that they were measured at, because we said that temperature affected rate constant, we can work out these terms. You've got these equations in your data booklet. So you can either, if you've got a range of data, you can do that plot, you can do that method, 16 point, well, sorry, this one here, or if you've just got 2 points, 2 temperatures, 2 rate constants, then you could solve this twice simultaneously. You'd end up with this relationship. So here's a practice question. Have a go at that. Temperatures, there's your rate constant K value. There's the answer. So first method, just using the 2 points, piling them into that, I get this value, and then if I do my plot, draw it out, take the slope, I end up with this. And as you can see, they're very different. So my maths, there might be a slip somewhere. You might want to check that. However, the theory is all correct, I believe. Quick note on these relationships, as you saw in the data used in that question, as temperature goes up, rate constant goes up, and this value of A is determined by kind of maybe how complex our molecules are. If you've got very simple, very small molecules, then we're going to get lots and lots of successful, potentially successful collisions. If we have very complicated proteins like our enzymes, then maybe that factor is going to be smaller because there's going to be less successful collisions. Great, that's that.